Today, you're going to learn how you can take a robot that has a Mecanum drivetrain and auto-align itself so that it can rotate towards any target of your choosing. As I hold left trigger and move, my robot is actually automatically rotating towards that target. I'm Brogan Pratt, and I've been teaching robotics and design for over a decade now. Today, I'm going to step you through how do you actually set up a PID controller so that you can drive a robot around, go forward and backwards and side to side, look at a target like something like an AprilTag using a camera, and how can you make it so that your robot automatically aligns itself and rotates towards that target, just like I am doing towards this camera now. I'm going to walk you through it all step by step. We'll start with the flowchart so you can understand how the logic works, with how you can write your own PD controller. We're actually not going to use I in this case, and why we might not want to use that. After we step through the flowchart so you understand how you can make this logic actually apply, I'll go and show you step by step how we can program this in Java. Now, I am going to show you how you do it in an FTC context with an AprilTag using a standard webcam, but I promise you that this logic can be applied in any other concepts, whether it is Python, whether it is an FRC program, whether you're using a Limelight. It does not matter. This is simply the logic reasoning that you need, and the only things you need to know is what is your angle towards that target. Now, a quick disclaimer, this is not a tutorial on how do you drive something with Mecanum. This is not a tutorial on how do you actually read an AprilTag. If you're looking for tutorials on how to read an AprilTag or how to drive with Mecanum Drive, I've got full tutorials on how to do that down below on my channel. So I assume that you already know how to read an AprilTag and you have some valid readings. And I also assume you already know how to have a Mecanum Drive chassis set up. So let's get into the flowchart and how we actually step through this logic. So whenever we start with a more complex programming challenge, we always want to start with a flowchart so we can understand how our logic works. So we're going to start off with the start loop section, and then the sort of flow that we're going to do for our program here is robots are sensing, thinking, acting machines. So we want to sense any sort of sensors, variables we need at the start of our loop. Then we can do with our thinking, any sort of logic that needs to happen. And then we can act, which is actually going to actuate the motors down the bottom at the end of our loop. So knowing that kind of knowledge, so the very first thing we have to do is we have to get our Mecanum drive setups. So eventually what we want to do is we want to be able to drive around with our robot going forward and backwards and strafing left and right using the left stick, and then rotating with the right stick. Or if we're holding left trigger down, it automatically rotates for us. That's the goal that we want to be able to do. So to be able to do that, we need to get our Mecanum commands first. So the very first thing that we're going to do is we're going to get forward, strafe, and rotation from gamepad. This is kind of one of our readings of our sensors. And we're going to get the rotation from the gamepad first so that if there's no AprilTag or if we're not holding down the left trigger, we can still allow ourselves to auto-rotate. But if we are triggering, we're going to update that rotate variable. Then we need to know how far away we are from that current angle of X away from where we are. If you're using a Limelight, this might just be your TX. If you're using a FTC or FRC just standard webcam, then you're going to have to grab the bearing from the pose object. So we're going to say get camera bearing to TX. So whatever our current angle is, how far away we are. Then if there actually is some sort of valid reading, we can also go ahead and calculate our error now as well. So our error equals our goal minus our current TX. So whenever you're calculating error, you want to think about where do I want to get to where do I need to be. And sometimes this error can be something like offset. So if your camera is set up slightly to the side of your robot, or if your camera's on a slight angle, or if you find that when you're shooting or the target you want to go to, you actually want to be a slight offset, you can end up setting your goal instead of being exactly 0, your goal could be -2, it could be 1, it could be -0.5, whatever it is that you need for that. Now comes our main decision in our loop here. Our main decision is that left trigger pressed, or whatever it is. If you're holding the B button, whatever it be. So we could say something like, is left trigger? And if our left trigger is false, we're just going to go back to our main loop. And in our main loop, we're simply just going to drive with our standard rotations. So here we're actually going to say call drive with forward, strafe, and rotation. And we're going to say this is false. So if we happen to be false, we're just going to call our drive. So if we go through our loop right now, we get our forward, strafe, and rotation from our gamepad. We get our current camera bearing, how far away we are from that angle of X. We set our current error. And then we check, hey, is that left trigger pressed? If it's not pressed, we just drive normally, and you can use a standard rotate, which of course would be that rotation from the gamepad. If it is pressed, here's where we actually need to start getting to our logic. So let's say that this is true. Now we need to actually start getting to the logic of our PD controller. I find I is probably not necessary here. Feed forward's also probably not necessary here. So we're going to start making our PD controller here. So the first thing we need to check is that ID valid? You could have multiple AprilTags that you're trying to get to, and you may want to check and ensure that you're grabbing from the correct AprilTag. So in my case, for my example, the AprilTag I'm using is ID 20. So I'm going to say ID 20. If this is true, we continue on. If this is false, we actually go back down and we do our standard drive, because we don't want to auto-rotate towards an AprilTag that we actually don't want to look at. So in our case, if ID 20 is true, we're going to keep going down. Next up, we're going to check if our auto alignment's already close enough to the target. So we need some sort of angle tolerance, because you probably don't want to be exactly straight on to 0, because if I were standing right here, this is still good enough for my target. And it's going to be up to you to decide what is that tolerance you need to be. So for instance, right now I'm standing directly in front of the camera. I could also have a 0.2 or 0.3 degree over here and a 0.2 or 0.3 degree over here. You can still see me. But once I start to get over here where I'm start talking about 10 degrees, or my angle tolerance is 10 degrees, now my tolerance is too great and I'm no longer on that camera. So what you need to check is if the error is within that absolute tolerance range that is you want. So next we're going to check if the absolute of error is less than our tolerance. This is another decision. If the absolute of our error is here, we're actually done rotating, because that means we are on target. So we're going to say, if this is true, we're going to set rotate equals 0. And then we will come back down to the main loop so that we can come back down to that main drive section. Because if we're within the tolerance where we need to be, there's no need for us to rotate this camera to be able to look towards things. We don't want to rotate. We actually want to stay where we are. So we're not going to rotate. If this is false, we're actually going to do a little jump over here, because I need a little bit more space to be able to continue showing this. The first thing we're going to do is we're going to calculate our P controller, how much our P value is going to be. This is a proportional error that you're going to apply. So your proportional control is higher the further away you are from your target. So if I'm trying to get my whiteboard to the pen, or to the whiteboard board, the pen to the board, the farther away I am, the faster I can go. The closer I am, the slower I want to go. So the further you are, the higher that P value is going to be. The closer you are, the lower that P value is going to be. We're going to talk about how do you actually tune that KP later, but we'll get to that. So we're going to set our P term is going to be equal to our error multiplied by our KP, and that is our proportional constant. Next up, we start doing some derivative control. And derivative control is kind of a damping force. So the closer I get to the target, I can have really high P, but what can happen sometimes, so let's imagine I'm trying to get this pen directly in the center of my nose. If I start from over here, I might start going really fast, and if my P is too high, I might actually overshoot. But if my P is too low, I might go really slow. So what I want to do is I want to have still a high P, so I move quickly, but the closer I get to the target, the more I start to slow down. So the derivative control, and what that allows you to do, is it allows you to have a little bit of damping force. So as I come up and go really fast and then slow down. So you already intuitively know how to do derivative control just with your own body. You're just not thinking about how it is that you're doing it. So how derivative control works is you get the current time, you get the last time that we read the last error, and then we can calculate the difference between those two, or that delta time. So for example, if it took you, let's say it takes you 1 second to do a single loop. That'd be really slow, but we'll just use 1 second as an example. the last time you read, you were here, and this time you're here. There's a huge gap between these two, which means you're going to apply less damping force as you go. But the closer you get to the target, let's say your next reading was here, and your current reading is here. That means you're starting to get really close to your target because your proportional control is now slowing down. So you're going to start applying more derivative damping so that you slow down even more. So the idea is the further away that the two last readings are from the last reading to the current reading, if there's a big difference between those two errors, you should apply less damping. If there is a little difference between those two, you should apply more damping so that you can get closer to your target and slow yourself down. So we're going to get the now time. After we get now, we need to calculate our delta time. So delta time is, again, just change in time, is equal to now minus the last time that we read a reading, or we got an error. Then we need to calculate the actual D term, the part we're actually going to apply. So we're going to say that our D term is equal to our current error minus our last error divided by our delta time, and then multiply all of this by our KD, or our derivative constant. And then lastly, to pull these things all together, we can actually start doing our main application where we actually tell our rotate how much we're going to do. So now we're going to say that rotate is equal to our D term plus our P term. And in this case, we're actually going to clamp this to something like 0.4 or negative 0.4 and 0.4. And when I say clamping, it basically means that if we return a value that's more than 40% of our max motor output, we're actually going to slow it down. Because depending on how fast your robot likes to rotate, you might not want to rotate at 100% power because you're going to overshoot no matter what happens. So even if your proportional or your derivative is really high, your error is really high, you won't have this huge spike in power. And then at the end of this, we're going to set last error equals our current error, and our last time equals our current time, or our now. And in this case, we now come back into our main loop, and we call our drive and our rotation. Now, there are a few more things we're going to add to this, but let's step through this logic quick first before we keep going. So let's imagine that we do not see a target present. There's no AprilTag in where we are. We're going to get our forward strafe and rotation from our game controller. We're going to get the current camber bearing. We're going to calculate our error, whether it actually exists or not, if we actually had something. Then if the left trigger is not pressed, we're just going to use our standard rotation from our gamepad. If the left trigger is pressed, let's come on up and let's check. Did we read the correct AprilTag? If we did not read the correct AprilTag, we saw something different, we come back down and we go back to drive, and we still have standard rotation so that our driver can still rotate towards our target. If it is the correct AprilTag, we're going to check, hey, we're in auto alignment mode now. Are we already aligned? Is our error less than our tolerance for success? If it is, we set rotate to 0, we come back. That still allows us to do forward and strafe from our gamepad control, but rotation has now been overwritten, so that rotation is now 0. Let's say, imagine we come back through the loop and we're no longer on the target. We need to start auto-rotating. Now we come up. We grab our current proportional control, which is going to be our error multiplied by our KP. Then we get the current time. We say that delta time is now minus the last time. This is how long it took for us to read our last loop. Then our delta term is our error minus our last error divided by delta time multiplied by our KD. And then to be able to actually create whatever that motor output is going to be is rotation equals D term plus P term, or clamp from 0.4 to negative 0.4 to positive 0.4. Then we overwrite our last error and our last time, and we come back over here where we now apply rotation, which was whatever was the addition from our derivative term and our proportional term. Now, if you remember, I said we're actually going to come back because there's one thing that we didn't do here. If the ID is not 20, something that can happen is you can have what's called a really large derivative spike, because right now, our last error and our last time are only getting calculated if we actually did a standard rotate, but presently they're not. So what we need to do is we need to set both of these so that if our rotate is true, We also have our last error. Let's just call this, block number 3. This is block number 3 that we need to do. And then same thing here. We need to do block number 3 before we come back in. And that's going to stop those derivative spikes. Because what happens is if there's this huge difference between the last error and our last time, because we haven't held left trigger for a while or whatever have you, we're going to end up with a really huge derivative spike. We need to do the same thing here. If it's no longer left trigger, we also need to do block 3 or that last error and last time so that it doesn't cause this massive differential spike, or sorry, not differential, derivative spike when we come back into this. So I know that that is a lot to go through. I hope that that makes sense, and let's actually start programming this into some code instead. So looking at the code here, let's take a look at my April webcam really quick. You can go ahead and pause this, or if you'd like this code as a default, I've also got this down as a code snippet if you join my community down below, but otherwise you can pause this and run in. This is just a handy little helper class that allows me to get April tags from the standard webcam on an FTC. And it basically just returns me a specific ID that I'm looking for. So if I put in ID 20 on an April tag, it will give me that ID 20. One thing I will say is that while you are doing your April tags, you really want to have your exposure rather low and your gain really high. Because the lower your exposure is, the higher your loop times are. The higher your gain, the more likely you are to be able to actually see the April tag in that concept. I find that this is a pretty decent value in a somewhat sunlit room if you're using a Logitech C20. Sorry, C270 if you want to go through that. Next up with the Mecanum drive, I just have my standard Mecanum drive set up with a field-orientated drive. And this is set up using IMU, and there's not really much to say. This is just a standard Mecanum drive class. So if you're not sure how to do that, I've also got tutorials on that down below. So let's go ahead and let's get started with a standard, with our alignment here. So I'm going to make a new class, and I'm going to call this one AprilTag Auto Alignment Mecanum Drivetrain. And then I'm going to put in an @teleop. And then I always like to extend the standard op mode because robots like to have things always in a loop rather than doing things in a linear. I prefer to program in a state-based machines. So our op mode always needs 2 standard methods. We need a public void init, and we need a public void loop. And now we're not going to throw any errors. So first up, we're going to bring in our webcam processors as well as a Mecanum drive or AprilTag processor. So I'm going to make a new private final, and I have mine called AprilTag webcam. And then this is the AprilTag webcam equals a new AprilTag webcam. And then I'll also make a new private final Mecanum drive. I'm going to call this one called drive. And this is a new Mecanum drive. Now, you set this up however it is you have Mecanum drive set up. I have it set up in a separate class. It makes life a little bit simpler for me. And I'm just going to keep going on this with the init because for mine, I also have the AprilTag webcam.init, and I pass in a hardware map, and I also pass in telemetry. And then for my drive.init, I also pass in a hardware map, and I pass in a Boolean to know if I'm using a go build a pinpoint IMU or not. Next up, let's start writing down some of our logic for our PD controller. And I like to have these set up with some dashes like so, because it makes it a lot easier for me to separate out my code. Remember, we write code for human beings to be able to read. We do not write code for computers. So let's do all the variables that we're going to need for that KP control or for that proportional control. So I'm going to set up a double called KP, and this is going to be equal to something really, really low at the start. Because if you can remember something with KP, you only have a maximum value of between -1.0 and 1.0. At least those are my motor outputs. If your motor output expects a larger number, that's also fine. But you probably have a larger KP in your case. Because I want to have such a slow rotation here, I might set this something really, really low, like something like 002 might be something. You might even need to be 0002 as a starting point for your KP value. But I'm going to set mine at 0.002 as a starting point. We also need a double called error, and we're going to set our error at 0 initially. We also need a double called last error, and this is also going to be at 0. That's going to set up for our derivative control. We also need a double called our goal X. I'm going to set this up at 0, but here's where you could also add in an offset. You could set this at something like -2, -0.5, or 0.5, whatever it is you find you want your offset to be. You could add in your offset here. If you're just going to make it 0, you don't really need a goal X. Some people call it target X. Wherever it is you want to get to. Then we need to know some sort of tolerance. So I'm going to make a double called angle tolerance, and I'm going to set this to something like 0.2. If you are using a webcam that is not super accurate, the less accurate your webcam is, the larger this angle tolerance need to be. Same thing with how close you need to be on that target. If you have a really wide target, there's actually no need to be this accurate within half an angle. The further you are from the target, the more accurate this has to be as well, because as you get further away from the target, your tolerance for angle being off is obviously less. And then we also need a double called KD. And we're going to set this something to like 0.001, so something really low, even lower than our P control. And then we also need a double called cur time, which is going to be equal to 0, and a double called last time, which is going to be also equal to 0. So this is going to allow us to set up for the D control. Now we have that all set up, we can do setup for our driving setup. And for our drive, we need 3 different variables. We need a double called forward, strafe, and rotate. And then something that you don't need to do, but I do like to do, is controller-based PID tuning. If you're in an FTC context and you're using panels or FTC dashboard, you technically don't need to do this for parameters. We're going to set up a couple parameters here that allow us to just update these on the fly. Use a controller. You don't actually need to do this. So I'm going to make a new list called step sizes. And this is going to be equal to 1.0, 0.1, 0.001, 0.0001, so that we can tune our P controller a little bit better. And we're going to call a new int called step index. And our first step index is going to be at 2, so that we start off adjusting our D at different points. Effectively, this is going to allow us to later play with the joystick or the gamepad to be able to up and down the step sizes for our KD and KP, so we don't have to rebuild this code every time we want to test a new KP or a new KD. Now, after we've initialized all the hardware we need to do, I also like to have telemetry add line, and I like to add in something like initialized, so that we know that we've actually got our robot set up. It's ready to rock to be able to get into our main loop. Now, before we actually start, because we're grabbing things like current time, we need to be able to reset our current runtime. So I'm going to have a new public void start. And inside of this start, we're going to call reset runtime, and then we're going to call cur time is equal to get runtime. That just allows us in an FTC context to figure out what now is. If you're using Python, it's probably, time.monotonic. Now, inside our actual loop, robots are sensing, thinking, acting machines here. So the first thing we're going to do is we're going to get Mecanum drive inputs so that we know what our current Mecanum drive is going to be. Oops, that should be indented one more time. So in this case, I'm going to say that forward is equal to gamepad1 dot get gamepad1 dot left stick y, and this is actually going to be negative because in an FTC context, your gamepad y is actually negative. We're going to set our strafe to our gamepad1 dot left stick x, and then our rotate is equal to gamepad1 dot right stick x. Then for my helper class, we're going to actually grab our AprilTag. So we're going to get AprilTag info. In this case, for me, I have an AprilTag webcam.update that I call every single loop. And I have a new AprilTag detection of ID 20 because that's what I'm going to be reading. It's going to be equal to an AprilTag webtime.getTag by specific ID, and I'm going to call in the ID 20. Yours might be slightly different than this, but this is what I'm using for my helper class specifically. But in any case, here's where you would actually get your AprilTag. If you were using a Limelight, it might say, limelight.getX or getTX from that. So now we're going to set up for our actual main auto alignment. So auto align rotation logic. And if you remember, for me, it's going to be all based off that left trigger. So I'm going to say if gamepad1 dot left trigger is greater than 0.3. I'm going to say greater than 0.3 because I don't want to have accidentally grab this. That means we have pressed that trigger. Now we need to check on that flowchart. We need to see, did we actually get the ID from that AprilTag that we want? So I'm going to check if we actually have that. So I'm going to say if ID 20 is not equal to null, because in my case, this method here will either return a valid reading or it will return null. So we're going to check if ID 20 is not equal to null. That means that we are actually reading an AprilTag and we are pressing our left trigger. That means we actually want to do our auto alignment. Now we can calculate our error. So our error is equal to our goal x minus rd20.ftcpose.bearing. So this bearing here is basically my tx if you're using a limelight. And this is the angle that I am away from that target. Again, not always necessary to say goal x to have 0 minus, but if an offset, it's really helpful. When you're calculating error, it is where you want to be, subtracting where you are. For the most part, there are a few cases where it's going to be the other way around. For the most part, this is how we typically calculate our errors. Next up, we need to check if we are still inside this auto rotate, and we want to auto rotate if we're already on target. So we're going to say if the math.absolute of our error, absolute of our error is less than our angle tolerance. If we are less than our angle tolerance, that means that we are within our range and we should set rotate to 0. Otherwise, or else, now we actually do our main proportional controls. We're going to make a new double called p term, and this is equal to error multiplied by our kp constant. And now we can start set up for our derivative controls. So we're going to say that cur time is equal to get runtime, so we can figure out what our actual reading is now, because this is the time where we're actually going to do the next reading. We need to calculate our delta time. So a double of dt, or delta time, is equal to our cur time minus our last time. Then we can actually calculate our d term. So our double of d term is equal to our error minus our last error divided by our delta time multiplied by our kd. And now we can actually reset rotate, or write over rotate, or set rotate. So we're going to say that rotate is simply going to be equal to our range.clip, and this allows us to simply add in our values here. So we're going to set our p term plus our d term, and then we want to never rotate any faster between -4 and 0.4 in my case. You might need to have slightly higher rotation values than this. You might have slightly lower rotation values than this. And then we can set up for next logic, which our last error is equal to our current error, and our last time is equal to our current time. Now, if you remember, we get these really huge differential spikes if this is the only time we call last error and current error. So after this ID null here, if we fold this back up, we're actually going to write an else. So if this ID 20 is not true, we're going to say else last time is equal to our get runtime, so whatever we're currently reading, and then our last error is equal to 0. And it's not necessary here, but just to, as a quick reminder here, we can also simply set rotate is going to be this same value here as rotate. So not necessary to put in there because we haven't actually overwritten rotate anywhere, but you can, grab another reading of GameStick X if it makes you feel more comfortable. It's not going to make any change to your code. Then same deal to help prevent some of those differential spikes. If our gamepad trigger is not pressed, we can have another else. And same thing, we're going to also set our last error to 0 and our last time to our get runtime. You're also welcome to using an elapsed timer for this. I prefer just to use the standard runtime because it's not actually necessary to have an elapsed timer. Now, all at the end of this, it's time to actually finally drive our motors for our Mecanum section. So now we can actually call our drive method, and we call this with forward, strafe, and rotate. Now, at this point, you're done. You can actually go ahead and test this and start tuning some of your KDs, your KP and your KD. To be able to make this a little bit easier, we're going to use our step index that we did up above. And I'm just going to paste in some code I have for my example here. So if I press the B button, I'm just going to cycle through that step index. So it allows me to change my P values by 1.0, -1. Actually, no, I'm going to even take 1.0 out of there completely because I'm definitely never going to use 1.0 in this context, but you could add a few more steps. And that'll allow us to change that step size. Then I have some quick logic here that if the left D-pad was pressed, we can decrease and increase our KP respectively. And with our up and down, we can increase and decrease our D respectively, just to make life a little bit simpler if we're going to do that on a gamepad. And then I like to give a few telemetry updates for myself here, just because I always like to give myself lots of data. So I'm going to say that if we currently don't have, or if we currently do have an ID for AprilTag 20, I'm going to say if our gamepad 1.left trigger is greater than 0.3, 3, not 2, we will do our standard auto align. Otherwise, we're just going to print out what our current data is and then our error. Otherwise, we're going to set ourselves up as, we are in manual rotation mode for that. Then I'll just simply add in what is my current KP, what's my current KD, and then what is my current step size so that I can see this out on that telemetry object. So that's it. That's how we actually set up. I know it's a lot of steps, but let's get into the tuning process, because tuning your KP controller is as much a science as it is an art. And I'll try to give you some tips as we go in and start tuning this. So let's build this on our controller and let's go take a look at this out on the actual field. Okay, so looking at our base setup here, we've got I've got a standard Mecanum chassis here. And I've got an AprilTag with ID 20 on the back, and I've literally just taken a zap strap or some zip ties onto the front of my robot here. It's probably going to reduce some of my accuracy because it's not a solid mount. So if I have a bunch of moving around, it's probably likely because of that. You should definitely have yours mounted a lot more stable than mine. So let's go ahead and let's initialize our auto alignment here. I click Init, and I'm setting my exposure. And now I'm ready to rock. And when I click play here, if we take a look, we can see that I'm currently seeing it. If I were to rotate myself out, I'm currently still seeing auto align. If I hold left trigger, you'll notice that I start to jump all over the place as I am moving, which is not exactly what I want. So let's actually start with tuning some of our KD here. So I'm actually going to turn the D controller completely off. So I need to change my B button for my step size, and I'm going to have no D completely here. And I like to start tuning with turning off D, because it's possible that having too high of a D is actually causing us to lose ourselves. And it looks like that actually was the case, because as I hold down left trigger here, you'll notice that it auto-rotates. So I'm going to move out of the way a little bit. I'm going to auto-rotate, and it rotates back in. I'm going to move out so it can see it. It cannot see it presently. It's now capable of seeing, so if I hold left trigger, it now auto-rotates in. So now I can use up and down, left and right, to actually start changing my K value or my P value. And what I want to do is I want to change my P value to such a point where I actually no longer overshoot. So I'm just going to jack my P up really high and watch what happens. As I left trigger, see how I'm actually kind of jumping over. I'm going to left trigger again. See how I'm actually going past my target? That's not what I want. So my P is actually too high. So I'm going to bring my P down to something like 250. I'm going to move myself back, and you can see that I'm still overshooting a bit. So I think my P is still a little too high. I'm going to bring it down again. You can see I'm still overshooting. We'll bring down something like 1.9. And we'll bring ourselves out a bit. And make sure my webcam can actually see it. And I want to have a point where I can still see the webcam in my target. So the furthest away that I can be, while still seeing webcam, my webcam's view is not wide here. I'm pretty happy with that. I'm rotating pretty quickly, but I'm not getting too far away from that target or not overshooting. So now we can actually start adding in some D. So I'm going to bring my step size down to 0.0001, and I'm going to increase my D to 0.0001. So now I can have a little bit of damping, so I can still move nice and quick towards my target, but I have a little bit of damping that happens as I move. And honestly, 0.001 seems pretty high, or seems pretty good. Because if I have too much D, let's increase that derivative control, and let's make it something really high, you get into like 0.1, you'll see that I'm going to start doing this kind of jitter back and forth, which is not quite what I want. So that D is too high. I think in my case, 0.0001 is probably actually a pretty happy D. So what I can do now is I'm actually going to hold the left trigger. I'm going to auto align, and I'm actually going to start rotating and driving. And you can see that my robot, as I'm holding left trigger, and I'm having a really hard time, my drivetrain's really fast. As I hold left trigger and move, my robot is actually automatically rotating towards that target. And I can actually move a little bit faster, and I'm still able to forward strafe, and I'm still rotating onto that target pretty quickly and pretty accurately onto that target. And as soon as I let go of left trigger, I can now get back onto manual rotation control and start moving myself in and so. So I hope you found that a helpful tutorial in being able to auto-align your robot towards a target using Mecanum Drive and some sort of April webcam. If you're looking for these code snippets yourself, you can consider joining my community down below, where I've got these things pre-written out for you. Otherwise, best of luck out there with assembling your robot, and best of luck with your auto alignment and your PD controller tuning process. Last thing, don't forget to, once you have your PD controller set, you need to go back and you need to update your code so that you save in those values, so don't just leave it right away. And as always, best of luck out there with building your next robot.